Okay, let's get started. I'm Wei Wei. I will be talking about the deep ranking models. Um, Firstly, I will go through the agenda. Um, the first thing is about the traditional models. It mainly has two parts. The first part is about the ranking features. For example, here um, we can extract a lot of features from the query document pair and then compute the score as one for the document. And then followed by the learning to rank module. Um, on the right side, this is an example of the pairwise ranking. We can compute a score for the first document and then the score S2 for the second document. The learning to rank input is only the score. It's only the scores. Then we will transit to the deep network-based ranking. Um, for deep neural network ranking, most of the world will leave the learning to rank loss as it is and focus on how to compute the score for the query document pair. There are mainly two types of networks. One is called Siemens network. So the query embedding and the document embedding are independently generated. The other one is opposite. It's called interaction-based network. So there is a lot of interaction between each word in the query and each word in the document. At last, I will briefly introduce a very successful model, wide and deep model, and this one is mainly used for the recommendation systems. Okay, the traditional ranking features. Um, So originally, people always use the handcrafted features. There are mainly two types of features. The first one captures the query document matching features. For example, the cosine similarity between the query and the document title, and some entity matching features. So the entity is actually the output of the NER component that Junshi has just introduced. Also, you can collect some click-through data um, from the search log. The second type of feature is the document alone, how popular the document itself is, and for example, number of incoming links and number of outgoing links. So this type of features is capturing the prior knowledge of the document without knowing what the queries looks like. So for learning to rank laws, in the beginning, uh, people are using the point-wise ranking. Basically, it's just a binary classification using the logistic regression, and this is the objective function, which is a sigmoid function. The S is the query document score. However, in the ranking is more about the relatively position of one document over another document rather than a binary classification. Therefore, um, the pairwise ranking is proposed. This is the objective function. We can rewrite it so that it's more clear. It's just a softmax function over over the two document, assuming the first document is clicked. In some other cases, the listwise ranking performs better than the pairwise ranking. The intuition is that since you are ranking all the documents together, you should consider all the document in one objective function. So the listwise function actually, listwise ranking objective actually takes a very similar form of the pairwise ranking, except that the denominators has all the documents, and then you can multiply it by the label, and this is basically a cross entropy function. So that's a very brief introduction of the traditional method for the ranking, and I want to focus on the. I want to I'll summarize the deep neural ranking first. Firstly, it will only focus on computing the query document score. So the learning to rank loss is untouched. And then there are two categories of the network. So we will start with the Siemens network. So the deep structure semantic model is one of the earliest model to applying the deep learning into the ranking model. So the input is two vectors, high dimensional vector, the query and the document. And let's say the vocabulary size is 30K, then it's a very sparse vector. And then you can get the sum of the word embedding of all the non-zero values in the query and the document. And then apply the feed-forward network. Finally, you can compute a cosine similarity score for the query and document. So the 128 embedding is the representation of the query or the document. One weakness of this approach is it's using the back of words representation here, and the word sequence is not considered. So the next work proposed to use CAM to model the word sequence. Now the input becomes too different. The input is a D by N matrix. D is the number of dimensions in the word embedding, and N is the length of the query, or on the right side is the length of the document. Again, applying CNN to reduce it to a fixed length of the vector, and feed forward, then get the cosine similarity value. So that's the Siemens network. We can see that by generalizing the text into a fixed length vector, it can do the semantic matching very well. And also it could be very efficient because the document embedding can be pre-computed. In the online setting, you just need to compute the query embedding. The disadvantage is that some of the lexical features could be lost, especially the people name or the company name, and also the rare words. For example, if the query is jobs at LinkedIn, you will probably get a lot of job-seeking documents, but not specific to LinkedIn. So this is caused by that in the Siemens network, it only used 128 embeddings to summarize all the information in the original text. Therefore, there are some information lost. Motivated by this drawback, the researchers has proposed the interaction-based network. So here I'm just showing one paper about the interaction-based network. I'm still going to use the previous example, LinkedIn jobs at LinkedIn. So the 3 dots means to represent each word in the query. And then we have a document. And let's say there are 10,000 words in the document. And then the first step is for each query word, compute a similarity vector. So each of the similarity vector has a length 10,000 because it's the cosine similarity between each of the query word and each of the document word. So this is where the interaction happens. As you can see in the beginning of the network, everything is coupled together. So there is no independent query embedding or document embedding. So the rest of the network is about how to compute the score. Based on the similarity vector, you can compute a histogram on it. The histogram can be the maximum value in the similarity vector, the minimum value in the similarity value, and the mean value. And based on that, you can compute the score Z1 for the first word, Z2 for the second word. So the Z here means how relevant the document is to the specific word. To compute the score for the whole document, you can simply do a sum of the words. However, the author did one step further. So the intuition is that the jobs at the query jobs at LinkedIn, the at should be less important than the other words. So what they do is they use a gated network to compute the weight for each of the word. And then the final score is the weighted sum of the Z value. So this is the summary of the ranking neural networks. Um, as we can see, it only focus, most of the work focus on the query document scoring. And all of them are end-to-end models, meaning that all the parameter updates are from the learning to rank loss. There are two popular architecture, Simon's network and interaction network. Simon's network is better at topical matching, while interaction network is better at lexical matching. The latency of the Simon's network is obviously much smaller than the interaction network. So in fact, in LinkedIn search, we are using the Simon's network. At last, I will briefly talk about the wide and deep model for the recommender system. So this is the white part. So you can think of it as the traditional method. It's just a logistic regression. So in the recommender system, there is no query. However, the query is simply replaced by the user behavior and the user profile. So some of the features could be the user last read document topic, whether it's sports. And also the feature could be cross feature. The sports feature and cross the document ID is 100. So they want to recommend this specific document to the user. And here is where the deep deep part comes from. For the entities, you can simply concatenate all the entities into one long vector and then apply a hidden layer and then contribute to the final score. So everything is trained together. So I just mentioned some representative work. For more work that is related to the topic, you can go through the references. Okay, that's all for the document retrieval and ranking. So next, I will talk about the language generation for assistance. It will cover four topics: the autocomplete, query formulation, spell correction, and the conversational recommendation. So for the first three topics, it's about search, and the last one is about recommendation. We can look at the common part of these four tasks. So different from the query understanding and ranking. So the language generation for assistant components, they have an additional goal, that is to improve the user experience. For example, in the autocomplete, we want to save the user strokes. And in conversational recommendation, we will use conversation to get more information. And this is done by actively interact with the users. So in the search related, all the components are providing more suggestions or feedback to the user. And in recommendation, the interaction is conducted by conversation. In terms of the modeling, all of them has a common part, that is the language generation. In terms of the difference, some of the tasks only focus on the word modeling, like the query formulation or conversational recommendation. Some other task has a higher standard that you have to model the characters and the words at the same time. The generation model is also slightly different. Uh, Autocomplete only use language modeling, and the other several ones use sequence to sequence. So let's get started with the first task, query autocompletion. The goal of the query autocompletion is to save the user keystroke by predicting the entire query. So this is an example SOFTW. It is not enough to just predict the software, but instead the system should predict the whole query, software engineer salary or software engineer. There are mainly two challenges. The first one is it has a very limited context. The words in the there are only 2 or 3 words in the query. Therefore, it is very hard to extract features for the query autocompletion. And also, the other one is the latency. So, autocomplete is probably the search component that has the highest requirement on latency. For each keystroke, for every character the user typed, we need to return the autocomplete result within 100 milliseconds. So in terms, I would like to go through the agenda for the traditional method. In the traditional method, it's all split into two steps. One is to generate the query, the complete query, candidate generation, and the other component is to rank it. In the ranking framework, because there are very few features to extract, people resort to context and personalization. Okay, candidate generation. This is an example of the candidate generation. The 150 is the frequency of the completed query. So the first step you need to do is from the search log, collect all the completed queries, and then compute the associated frequency. Now you need to, for any prefix, you need to efficiently retrieve the most frequent queries. So what you can do is you can implement a try data structure. So with this try data structure, the most frequent candidate can be retrieved within 1 millisecond. One issue is the search, because all the complete query is from the search log. Maybe the search log does not contain enough prefix. For example, if the prefix is cheapest flights from Seattle to, it's unlikely that it exists in the existing search log. So what you can do is to remove the previous words and only start to complete from the 2. One issue with this approach is that there may be very few queries that start with 2. So the idea is you can build another try only on the suffix. This is an example of the query distance from Seattle to DC. The suffix are the from Seattle to DC, Seattle to DC, and to DC. So this try is only focused on the suffix. So when there is no prefix matching, then you can use the suffix try to do the completion. Now we come to the second part, second step, which is the candidate ranking. Given some candidates, you want to re-rank it. So the challenge, as I mentioned, is there are very few reliable features you can use. The most useful is the frequency. Of course, you can extract some features like CTR, but they are overwhelmed. The model is mainly dominated by the frequency. So that's why people has resort to the context-aware approach. The idea is the context here means the previous query or the queries in the same session. The idea is to re-rank the candidate by identify the most similar candidate to the previous queries. So this is an example of the prefix infant, and currently we have two candidates: infant Nike shoes and infant nutrition. And one of the previous query is baby eating disorder. So so the problem is reduced to how to identify infant nutrition should have a larger similarity value with the previous query. So at that time, deep learning is not very popular. So what they do is they added the similar words into the original query to get a richer representation. So by doing this, they are able to identify that infant nutrition is closer to the baby eating disorder. The other type of work is tries to finding new features from the personalization. So this is an example when the query prefix is I. They found that for women the query tend to be Instagram, and men are likely to search for IMDb. Also, it is related to the age group. So all the feature lists are simply demographic features. So they are like the same, the frequency of the query um, that is from the same age group or same gender or same region. So that's the traditional method. In the deep learning method, it's very different. The first one is only targets on the ranking part. So they keep the candidate generation part as the original method. The second method is an end-to-end solution. So the language model is used, and also there is no clear line between the generation and the ranking. And later I will show how to in the language model framework how personalization can be easily incorporated. So the first method, applying deep learning only on the ranking part and keep the generation untouched. The idea is to measure the semantic coherence between the query prefix and the query suffix. So the input is a n by d matrix, and applying CNN, then get a cosine similarity. As you can see here, this graph is actually very similar to the ranking graph. The only difference is here it is the query suffix, and in the document ranking, it is replaced by the ranking. It's replaced by the documents. Now the second method is completely different. The idea is to use language modeling. And let me start with the training first. In the training, they are using a character level language model. So this is an example of the training query, completed query. And we are at the stage of T, and the next character is an empty space. The input, you can have a for each character, you can have an embedding. And then the embedding are feed into a LSTM. On that LSTM, there is a softmax over all the character vocabulary. Let's say there are 30 characters in total, then this is a classification over the 30-way classification. What are they classifying for? This is actually tries to predict the next character. So by doing this, the model is able to learn the correlation between the previous character sequence and the next character. They also incorporate the word embedding into it. Let's look at this example, the empty space. Whenever you see an empty space, it means that there is a complete word. So you can put the president as the word embedding. For the other cases, you can just use a special token, incomplete word. By incorporating the word embedding, they're able to get a better result. Also, I would like to introduce how the testing works in the language model for autocomplete. And during the test, you will see that the candidate generation and the ranking happens at the same time. Also, there are multiple iterations of the generation and the ranking. So the input is character B, and then for each character, there is a probabilistic estimation, and then choose the largest one to fit into the next as the input of next stage, and then generate another character, and then this whole process repeat until a special token, which means the end of query is produced. So one technical detail is that what I just shown you is a greedy algorithm. In fact, people use bean search. So this is a animation of the bean search. 3 candidates are generated, and then for each of them, generate again. For the 9 candidates, pick the top 3, and then repeat the process. So in reality, bean search performs much better than greedy algorithm, and in fact, no one used the greedy algorithm. So this is the for personalization. You can this is an example of the how to incorporate the personalization into the framework. The input could be the user ID, and if you want to incorporate features like gender, location, you can also do it this way. That's all for the personalization. There are some other complicated methods. If you are interested, you can read the reference. So recap for the query autocompletion. For the traditional method, it's very hard to extract features. And for the deep learning method, it's very flexible to incorporate variants of features into the same framework. It's an end-to-end solution, not only appearing in the training where all the parameters are optimized together, but also in testing, the generation and ranking are performed at the same time. There are some weaknesses of this approach, the language modeling approach. One is that it could be very time consuming. So to generate one character, you have to do a ranking. And then because it performs at the character level, it may generate wrong words. So in LinkedIn, actually, we are doing something like we only apply on the ranking part, not the generation part. This is the reference. And okay, the second topic is query reformulation. So in this topic, there is no modeling of the characters, and this is also one of the reasons it can beat the traditional method significantly. The goal of the query reformulation is to provide better suggestion of the query automatically. So let's assume a search scenario. A user search for FB developer. Maybe all the results are too general, and then the user did not find the desirable results. And then in this case, usually the user wants to change his keywords. So in this case, the system can provide the automatically reformulated query for the user, and the user can simply click on it and and saving the effort to think about new features, to think about new queries, new keywords. Agenda. I would I will use a very simple. For the traditional method, I will just introduce a very simple baseline, the collaborative filtering. The first step is to collect the training data. So the training data can be collected by the query pairs, which are issued by the same user from the search log. So our system wants to learn the reformulation pattern. And then the second step, you can treat each query as an ID and then build a query-to-query matrix. And the value in the matrix is the TF-IDF value. There are some issues about this approach. The first one is you are treating each query as a unique ID without looking at what are the words in the query. And because of that, there is a severe data sparsity. So for any long queries, the frequency is going to be very low. That's why, and then with low frequency, you cannot learn a good suggestion for the query. So that's the data sparsity issue. And also, obviously, you cannot generate new queries. For deep learning framework, the researchers has been using the sequence-to-sequence for the related search for the query formulation task. And then I will introduce two work. One is driven by the more by the application. One is more on the algorithm part, using GAN for sequence-to-sequence. So this is the sequence-to-sequence framework. On the left side is an encoder, is the previous query, and on the right side is the decoder. So you can see here it's also this part is also a softmax. It's trying to predict the next word, Facebook. And you can see here, the decoder here is actually a language model. And under this framework, all the word semantics are understood very well. The next paper is about conversational query reformulation. This is a work done by Microsoft Bing. They found that in the search log, there are a lot of so-called conversational queries. For example, here, the first query issue. So both of the query are issued by the same author, the same user. The first query is when was California founded, and the second query is more like a follow-up question about the first query: who is its governor? Because the assumption of the search engine is that it is stateless. Each query is an independent query. So therefore, the second query, usually you will not get the good result because the search engine doesn't know what does the it mean. What is more interesting about this data set is that the user will issue a third query, which is the summarization of the first two queries. So as you can see, the search engine can answer the third query very well. So therefore, the goal of this paper is to summarize the first two queries into the third query. The first method is very straightforward and simple, very intuitive. On the encoder side, you can just stuff the two queries, the Q1 and Q2 together. So it's a called concatenated sequence-to-sequence. The second one is attention over the two attention generated. So this is the first query. You can run an LSTM on it, encoder. The second query is also encoder. The third query now we are actually applying decoder on it. You can generate a context vector, the attention vector, for the first query and for the second query. And then the final attention is just try to combine the information of the two attention vector. By doing this, they are able to get a much better result. Okay, the third paper is about is more on the algorithm part. It's try to applying the GAN for the sequence to sequence. So this is motivated by an issue of the sequence to sequence. They found that there is some discrepancy of the training between training and testing in the decoder side of the sequence to sequence framework. So let me illustrate it where the discrepancy is. During training of the decoding, we only look at the decoder side. During training, the input of the decoder is the ground truth word. And however, in the testing, the input is the previously predicted words. So obviously, this will cause some worse performance because what you are training for is not what you are going to use in the real world. So the goal is to resolve the training and testing discrepancy with GAN. And so this is an example. I'm going to illustrate how GAN resolve the discrepancy. The original query pair is assume it is software to software developer. The GAN has two parts, the generator and the discriminator. Inside the generator is just the sequence to sequence. But here, it's using the testing schema. The input is the previously predicted words. So throughout the training and testing of the GAN, the sequence to sequence is fixed as it is. So this is how the discrepancy is reduced. Now we look at the discriminator. The first step of the discriminator is to copy the generated sequence and then copy the first query, the software engineer here. And because the software, the generated sequence is software UI, is different from software developer. So the discriminator should predict it as 0. So if in some other sampling iteration, the correct query is sampled software developer, and then in this case, the discriminator will predict it as 1. So that's all for the query reformulation part. We can see the sequence-to-sequence framework is very powerful because it directly modeling the words, and also is very flexible to incorporate any session information. It achieves great performance compared to the baseline. One of the reasons is there is no character modeling. And our next topic is about spell correction, which heavily involves character modeling and word modeling at the same time. Okay, this is an example of the spell correction. There is an O missing, and then the system should identify this and also identify the correct query and directly show the result of the correct query. Of course, it will be very helpful because with the spell correction, it will significantly reduce the no result, no search result cases. Well, assuming that when we have a wrong words on Microsoft without the O, there will be very few documents that contains these wrong words. So to build a spell correction system is very challenging because of two reasons. The first one is there are many rare words like people or company names looks like the misspelled words. This is an example. Both of the tumbler and tumble W is similar to the tumble, but the first one has no errors, but the second one is actually has errors. The same, because the Tumblr is a social media. The same applies to this query. S10E has no errors, and S10D has error. This is very domain knowledge specific. The reason is Samsung has such a model version, but do not have such a model version with S10D. And as I mentioned before, in the spell correction, you have to model the characters and the words at the same time. As usual, we will start with a traditional method. I will first talk about how to generate a candidate for a word, and then based on the candidate generation for a word, we can generate for the candidate for a query, and then followed by the ranking. So the goal of the candidate generation for word can be summarized by these two examples. Given tumble W, tumbler and tumble are correct candidates. However, given the tumble R, tumble is a correct answer, but tumble W is not correct, should not be suggested. So the problem is reduced to the challenge of what is a legit word, what is a correct word. That is, tumble R is a correct word, but tumble W is not a correct word. We cannot simply use a dictionary, such as Webster dictionary, because every day there are new correct word generated. So in this paper, the solution is to use statistics in the web noisy data. And the key idea is that the correct word should appear much more frequent than the incorrect word. So this is the detail of the method. The first step is to collect the term list. So this is a huge list with maybe 1 million words. And then you can apply edit distance to find the candidates. So the word pair is called confusion word pairs. For tumble R, the candidates is tumble W, and vice versa. This is not, so recall that ideally we want to remove the first item. So what they do is to filter the list, the word pair, by using the frequency of the context. The context could be social media. So the frequency of social media tumble W must be much smaller than the frequency of social media Tumblr. So, and then we are able to remove the wrong candidates. The next step is to generate the candidates for the query. So this is an example with two wrong words, ear and pain. You can apply the previous method and then generate candidates for each word. And then the candidate generation is simply, for the query, is simply all the combination. The problem is the query candidates grows exponentially with the number of words. And then their solution is to prune the second layer, the word candidates, by using a language model. So for each time, only one erroneous words, is replaced by the candidate, and then apply the language model. Therefore, a lot of the wrong candidate can be removed. Now this is again the second step, candidate ranking. By now, I believe you must feel very familiar with the features. Basically, it's just the similarity between the candidates and the query, edit distance, frequency of user reformulation, and the likelihood of the candidates. So this page is again very similar to the document ranking. This part is the query document similarity. This part is the popularity of the documents. Okay, we can move to the deep learning method. Again, the sequence to sequence is heavily used because it has a language modeling component that can generate new tokens. There are three architecture that is explored: word to word, character to character, and character to word. The first one is the word to word framework. Um, uh, Specifically, it should be from the subword to subword. The encoder side is the subword and the decoder side is subword. Subword is actually a technology to decompose the unseen words into existing word and some prefix and suffix. So for example, EARR is decomposed as ear and hashtag R. The problem with this method is that the subword is originally designed for the normal text without errors. But here we are actually applying it for the corpus with a lot of spelling errors, and the result is not going to be very good. So this is an example to illustrate why. So for hunter, you can, by applying subword, this is the normal text. You can, this is hunter and hashtag ER, and the subword is very relevant to the original word hunter. But with spell errors, the result is completely irrelevant. Because of that, so people has proposed to use another structure from characters. The encoder side is character, and the decoder side is also characters. The problem with this method is there is no word information encoded, and again, even though you are building a spell correction model, you can. It's very likely you will produce wrong words because characters. It's very hard for the model to generate correct words when when the token is characters. So therefore, the most popular structure is from characters to words. The left side is characters, and the decoder side is words. The benefit of this framework is that you can also leverage a very large pre-trained language model because the decoder side is a language model. Okay, so that's all for the three search tasks. The last task is about the recommender system, conversational recommending system. This is an example of the using conversation during the recommender systems. So after clarifying the sentiment, the system can recommend a better movie for the user. Why do we want to use conversations? Firstly, the system can actively gather more information or to actively resolve any ambiguity in the user utterance. So in this case, the sentiment is not presented, and then the system can explicitly ask for it. This is also similar to the active learning. And the second benefit is it provides better user experience because humans are very used to use conversation to communicate. The challenge also has 2 points. The first one is it is very hard to dynamically decide what to ask for the user. And also, the system needs to achieve a very good balance between asking a question and do a recommendation. So too many questions will definitely hurt the user experience, and recommendation directly um, may result in bad results. So the first method is also the traditional method that is based on collaborative filtering. The UI here is the ith user embedding. The VJ here is the jth item embedding, and the YIJ is the score for the items. And then in this paper, uh, the question generation is done by using a template. The template is fixed. It is always do you prefer x1 or x2, and the chosen of the x1 and x2 is based on the current recommender system, and then provide the user answer, and then to update the current model. Also, in this paper, the number of times of the update is fixed. For example, you always ask 3 questions before making the final recommendation. So there are obviously 2 issues. The question is generated by a fixed template, and because the update is always 3, so it's as you can see here, all the decisions are rule-based. So there is no direct modeling of the whether to asking a question or to recommend an item. So again, this is the researchers has proposed to combine the sequence to sequence into the recommender system. So the in the encoder side, this is the user input. I watched Forrest Gump before. And then apply a sentiment analysis module to extract the sentiment information. With the movie together, the movie and the sentiment is sent to a recommender system, and then a new movie can be recommended. However, on the decoder side, the system, the module find out there is no sentiment about the user input. The decoder decided to throw a follow-up question, do you like it or not? And throw away this recommendation. And then the conversation can go on, I love it, positive sentiment. And by using the new information, the recommender system can provide a better recommendation. So that's the method of combining sequence to sequence with recommender system. There is still one issue about this method. That is, only the sentiment information is encoded. Without, it's more about do you like the movie or not. It is not applicable for facets, such as whether give me a movie that is directed by Christopher Nolan, or give me a movie that is released, that is filmed in 2007. So the next paper focus on directly modeling these facets. And so they use something called belief tracker. The belief tracker will keep track of all the facet information solicited from the users. So this is an example. I want to find a Chinese restaurant. In the belief tracker, it maintains a data structure of all the facets. By based on this method, based on this utterance, the type of the restaurant is Chinese. And then all this information is fed into a policy network. The policy network is actually a classification to find out whether the information currently the system have is enough to make a recommendation, or it should continue ask for more new information. So here the system asks for the location information from the user. So this is how they this is the model detail. For the belief tracker, the input is an user answer, which is a natural language sentence. It is run through multiple LSTM. So here there is n LSTM. It means that there are n facets the system wants to track, and the output is is represented by denoted by f1 or fn, the facet information. It is worth noting that here the facet is actually a distribution, a probabilistic distribution of the facet. It's better to use a probability instead of a binary decision, because the language, the LSTM could be wrong about understanding the user language. So S is simply a concatenation of all this information. And then you can apply a policy network to produce a action. And the recommendation system also use the belief tracker output. Also, in this work, they use reinforcement learning to consider the future action. The future action could be, for example, here there are 3 paths. And then each of the 3 paths is evaluated by this equation. So the R is a reward and gamma is a decaying factor between 0 and 1. It means that the future action will be downweight. Okay, that's all for the language generation part of the 4 topics. I would like to give a brief summary. In the traditional method, it's always decomposed into 2 steps, generation and candidate. And the generation is rule-based, and in the ranking part, there will be very few features. The benefit of such a simple method is the latency is very low. For the deep neural network method, usually both of the 2 components are combined using an end-to-end solution, and all of them share the same language generation part, which is the language modeling, and the latency therefore could be very high. Okay, that's all for the first 3 parts. My colleague Huiji and Liang will talk about the real-world examples. Thank you.
Hi, I'm Huiji from LinkedIn. Thanks everyone for your attention, and thanks for staying with us so far. With all the excellent work presented about the deep NLP in search and recommender systems, are you all excited to see some real-world examples? Great. So I'm going to go through a few examples, specifically focusing on this topic at LinkedIn. Now let's first take a look at what are the search and recommender systems at LinkedIn. You may be familiar with this one, job search. Right? So job search is to rank job posts for users based on their submitted queries. So we can help them find the jobs they would like to apply for. Correspondingly, we also have job recommendation. And this job recommendation, we know that we don't have query, right? So we need to look at from the member's profile and the past behavior, and we can populate this recommendation through many channels. For example, we can through the feed, notification. Also, when you search a job, there's no result to show. We are going to show you job recommendation. Now, another topic, people. You can also find people at LinkedIn, different kinds of people. You can find people, specific people, or people with different properties, skill sets, or you can find people for recruiters to help them to find the candidates. And lead search. This is for sales. You can help people to find leads who are decision makers in company with potential buying intention. Also, we have people recommendation. Can recommend you with people you may know in the same role. Another example, content. You can search content, for example, last year's KDD event, it's showing here. You can also get recommendations from the latest updates about the content, right? We also have this KDD booth, by the way, and ads, a special content, promoted or sponsored by advertisers. This is also one type of recommendation. Now, with this introduction, I think you pretty much have a concept that LinkedIn does have rich natural language data. So I'm just going to give one example to show where are these natural language data. I use job search. First of all, we have query. Right? With job posts, let's take a deep look. At LinkedIn, some of the data, like job posts, they are semi-structured, which means we have structured data like title, industry, functions. We also have free text data, like job description, company description. Similarly, for content articles, you can see this is kind of free text data. And learning course, this is another recommendation system we have. This is also semi-structured data. And member profiles. Member profiles is very helpful for us to find a member, but it is also important, a crucial component for both search and recommender systems. Why is that? It represents member, right? Who make the search, who come for recommendation, so we can understand their intention from the member profiles. Here. So with that natural language data, as shown here, you may be wondering how LinkedIn considers these natural language components in our search and recommender systems. In the introduction, we have a brief overview about the search recommender system ecosystem. And here I'm going to give a little bit deep dive on these components, starting with search. What do we have search? We have query, right? Recommender system. We don't have query, but we have member profiles. Now let's take a look at. With query, what we can do? We can do online assistance. A set of components we have discussed, including spell check, autocomplete, and related or say query suggestion. Then we need to do text processing. Typical processing including language detection, tokenization, normalization, accent handling. And after that, it's very important. We need to understand the user intent. No matter you do recommendation or search, intent is very important. But here we have slightly different components because for query, it's more really focusing about the query understanding. So the major components are query tagging and query intention. For recommendation, we have profile understanding. Oh, sorry, it's a bit fast. Now, after we understand the intent, what we can do? We already show you candidate selection, right? But candidate selection, we also need to understand the other part. That is a big document corpus. We need to understand that. Then we have different terminology. Say for search, we usually say we want to do retrieval. And for recommendation, we say we want to do targeting. But pretty much the same thing. We just want to do candidate selection. The purpose is we can reduce the original large amount of candidates from here to a small, or say scalable subset. So we can do scalable ranking. Now from there, we can start multiple iterations. We can give users suggestions or give them some choice to make this become the conversational AI. This is the LinkedIn search and recommendation ecosystem. But although I have introduced so many natural language components at LinkedIn, there are a lot of challenges by doing that. The first one comes from the data ambiguity. On the search side, usually the query is very short. For example, ABC. What does this mean? Anyone can tell me what does this mean? If you search for ABC, yes, ABC can be company, ABC can be news, ABC stores, right? Because query is very short. Another example comes from the, actually, either query is short or we have the structured data, so we don't have enough context. Let's use this example. Being search engineer. If you encounter this kind of query or phrase, what would you think about? What does this mean? Intuitively, it looks like an engineer from Bing search, right? But it could have another interpretation. Anyone can give me one interpretation about this query, this phrase, Bing search engineer, in addition to engineer from Bing search. Bing is hiring engineer. Yes, that's one. You actually found another interpretation. I have one more. That's a search engineer whose name is Bing. oh, it's real data and a large amount of data in this kind of queries. Another one, personalization. Now let's say you have a query looking for new jobs. Intuitively, this is like you are a job seeker looking for jobs, right? But still, there could be another interpretation or more. Anyone can give me this example? It could be recruiter looking for candidates whose profile have looking for new jobs. That's also a lot of data at LinkedIn. We are seeing this kind of trend. Yeah. The second challenge comes from the deep semantics. This one we need to deeply understand the documents, so we can further interpret the member intention. One example is when you have a user profile, say in recommender system, you have a user profile saying that I'm a developer proficient at cloud computing. So when we do the recommendation, based on this context, we want to recommend something related to, for example, Azure AWS, either learning classes or jobs or content posts, right? But there's no such keyword match between these two. Another example, engineering openings. We should understand that this is job posts. So these are kind of example challenges of NLP in LinkedIn. But intuitively, we think deep learning can help. However, applying deep learning for NLP at LinkedIn also comes with challenges, a lot of challenges. I will just list a few. First one is the product-oriented model design. Basically, for deep learning method, we need to design this algorithm specifically for a search or recommendation component. But you know, we already showed you the complicated ecosystem. Each component is heavily connected with downstream and upstream, so by changing one, it will cause a lot of other effects. And coming to the product, we also need to consider business rules, post filters, blending, user experience. Some of them can be incorporated into the modeling, some of them cannot. So we have to make a balance between the modeling and the product. The second one is model debugging. You spend a quarter or 2 quarters, you had a model, you launch online, see, it doesn't work. And we cannot give up, right? We need to understand why. But we know deep learning model is very hard to interpret. Model understanding is a big challenge here once we encounter online performance issues. The third one, online latency, that's always a concern at the industry. How to save deep learning models with product latency, serving deep learning models with product latency restrictions. Many times, actually, we need to make a sacrifice to the model performance in order to have it running smoothly online. So with these challenges, we also have several ways to apply deep learning. One way is we can also do feature-driven. You can use whatever deep learning models to generate high-level features, then incorporate this feature into your current model, maybe a shallow model, say logistic regression or say tree model. The other way is we can do model-driven. We have the deep learning model power entire NLP component end-to-end. Which one do we think is more challenging? Which one do you think is more challenging? The second one, right? Because I'm going to talk about the second one. Okay. So just keep in mind, this is the ecosystem. Now, I want to classify those components a bit. We have NLG here for online assistance. And we have NLU here for intention understanding and document understanding. We also have matching here. If you still remember this figure, this is from technology perspective. We also classified major technology into 5 tasks and finally into these 3 categories. So in the following talk, I'm also going to align the applications with each of the category. Let's start with NLU, intention modeling. What is the intention model at LinkedIn? I'm going to introduce query intention. So the query intention, ultimate goal is to help user identify what they really want to do at a LinkedIn search. Say we have a query, and our output would be 2-level intentions. The top level intention is about which search vertical you want to look for. At LinkedIn, we serve different search verticals, as I already showed. We have people, job, content, classes. Second level is, now with these verticals, what are the specific properties? For example, if you are looking for people, what kind of people you are looking for. If we are looking for a job, what kind of job you are looking for. And in this example, he is looking for job posts from LinkedIn on software engineer position. Now, if we think this from a different perspective, intention modeling is mainly about task-oriented intent prediction. Every user comes to LinkedIn search looking for something, try to fulfill a task. And we can list all these tasks here. There are actually more. All the tasks here, then if we connect all the intent together, this becomes a member search footprint. This search footprint is not only helpful for search systems, it can bridge in the gap between search and recommendation. So you can recommend a user with some kind of content related to machine learning, like machine learning related job posts or content or news or classes, because this user searched for machine learning 101 a day ago or a couple of minutes ago. This is how we can bridge the gap. But due to the time limit in this talk, I will just focus on the top level, first level intention prediction. So given a query, we want to predict which vertical he is interested in. How would this be helpful? What kind of product we have? We have something called a search planning. In search top page, if you try LinkedIn, you type some query, you will see when we return, we actually return you a mixture of search results across different search verticals. So here, identify the intention is very important. And I'm going to show you this example. With the query here, we actually show like primary results is all about the people. And the secondary results is about the jobs. There are other kind of results. How to do that? Seems an intuitive classification problem, but it comes with challenges. First challenge is a complicated semantics. See this query, software engineer jobs. No doubt, this is a job, looking for jobs, right? How about Steve Jobs? No doubt this is the people, right? How about engineer openings? I have used this example, as this is a job. Right? Second challenge comes from the personalization. See, I have a query, blockchain tech. What is this about? It can talk about a lot of things. It can be looking for jobs, or looking for companies, or content, video, recruiter, even recruiter looking for these kind of candidates. We don't know. So in order to tackle the deeper semantics and the personalization challenges, we used one of the deep neural network model, CNN here. But why do we choose CNN? It is because CNN can capture n-gram features where, and in query, we do not have many long text. It's very short text, so n-gram is enough. And also, CNN provide a more efficient and also with generalization power, so we can easily incorporate other features, like member features for personalization. Here's how we do that. Now we start with, somehow it doesn't work. Okay, we start with query word. And then we organize them into a query embedding matrix. Then we start to use the convolution layer to extract high-level features with respect to different n-gram windows and with respect to different filters. And then we use max pooling to only keep most essential, most informative features and concatenated with other member features. So become one dense layer to represent the user's intention with this query. After that, we start to do application, like intent classification. This actually works well online, both online and offline. So offline-wise, we are seeing CTR lift on both job and overall clusters. The baseline is actually a state-of-the-art machine learning model. Now talk to the second topic, sequential tagging, still under the natural language understanding category. Entity tagging or sequential tagging at LinkedIn is very helpful for both search and recommender systems. So I'm going to talk one by one. In search systems, we know we have query, right? And with that query, I'm just going through a brief concept about the information retrieval, so just to bring everyone on the same page. With query, we also have a large result pool. We have relevant results marked as orange, and irrelevant results marked as green. Now, what we want to do is we want to first retrieve a subset here. Right? Then we are going to rank on top based on this subset. So the first part is about the recall. Second part is about the precision. And entity tagging or here for query tagging is going to help on both stages. How is it going to help? Let me show you. Let's say we have this entity tagging. We have first name. We marked this Mike is first name, LinkedIn is company name, software is title. Here are some short terms. So on the other side, we have indexing, right? Indexing, what we want to do is we want to say that document 1 to 4, they contain a term Mike, which is first name. Document 1249 contain a term engineer, which is a title. But how do we know these are titles? These are first names. Remember, LinkedIn has semi-structured data. So we already get this data from our like member profile or other places, but in some time, these data are not available. So we needed to apply the same entity tagging technology to get this information, maybe from the member's background, like a description or something. Right. Now with this entity information, then we can start to do a retrieval. Now with this query, you will see document 2 and document 4 will be retrieved. This is how it helps retrieval. It will also help for ranking because with the entity information, you can easily generate features between query and doc. That would be like is first name match or is title match. This is an example about search. Let me also show you another example about recommender systems. Ads recommendation. When we recommend content or ads to users, technically we cannot rank all the things at the running time, right? Even we can, we don't have to. But on the other side, when advertiser they release the content, they also want to specify the targeting. This is called advertiser targeting. They want to say that I only want my content to be visible to a subset of people, not everyone. And for example, to the people who have these kind of skills, or to the people who have these interests. Now, one question is, how do we know people have these properties? Yes, we do have member profiles, right? How do we know that? One way is, of course, we still have semi-structured data. We can get some of the information, but if they are not there, we will need to apply entity tagging on the, for example, experience, member self-description to identify this information, skill, interest, and then fulfill the functions. Now, this is how entity tagging can help in both search and recommender systems. How do we do that? Come back to the reality, how to do that. No matter you have a query or your sentence for recommendation or whatever, this is an example. Basically, we want to assign a tag to each word. The tag could be company name, title, or unknown. But we want to extend this label a bit with position information. For example, BCN means beginning of a company name. IT means inside of a job title. Now with that, actually Jun already gave a very deep dive about how entity tagging will work. And here I'm just using LinkedIn example to quickly go through that. So ideally we want to predict label for each word, and we will have handcrafted features here, and we can, one way is use logistic regression, we can just do this independent label prediction. Or we can use CRF to consider the label correlations. And then, because CRF is still using the handcraft feature, so we can use deep learning to do automatic feature extraction, right? For example, ASTM, we can do automatic feature extraction. Then use that to do prediction. And we can also use semi-CRF to consider the freeze level feature. So all these technology has been tested and experimented at LinkedIn. And what I'm going to share you is not about the results. It's more about the concept, the intuition about these. Here is just a brief like a performance overview with LinkedIn data. But I want to share you the deep and wide structure is not only a good concept for like ranking or something, it's also applied for entity tagging. So when we develop these automatic features, it can replace some of the handcraft features, but for some, we still need to be careful. Eventually, they can be complementary to each other. For example, freeze level feature is very important. That's why you see semi-CRF still has good performance. This is about entity tagging. Next, I'm going to talk about the NLG. So let's start with the encoder-decoder. We already discussed the application about query suggestion. Basically, it is to save user effort of rephrasing informative queries or capture user search intent. traditional methods use observed query reformation pairs or use based on the frequency or calibrate filtering. We know that one shot is its lack of generalization, so we cannot handle unseen queries. But from the modeling perspective, we are thinking about how user do the reformulation, right? When you type of query, you reformulate, basically you delete something and start to write something. This is more about the generation process. So we want to use a model to capture this generation process. That is sequence-to-sequence model we want to use. Yeah, technology-wise, I think we already discussed a lot. Basically, at the training time, each generated word is based on the ground truth, and at the testing time, it is based on the last prediction. So this will cause so-called exposure bias. Gain is one way to mitigate that, but another way is we can also use beam search to find the candidate sentence with the highest likelihood. That's one. But at LinkedIn, we also found some other challenges. Now take a look at this example. Two users, one is software engineer, another is accountant, and both search for Microsoft. Do we expect they receive the same suggestions? We don't, right? They have very different background. They should have different results. But how can we incorporate personalization information? There are many ways. Here I'm just showing you one way. So you can incorporate member-related information as one additional input to the sequence-to-sequence, right? But you can also do other ways. For example, you can concatenate it with other word embeddings and see how it works, case by case. Yeah. Oh, with that, we also have latency concern. Sequence-to-sequence takes a lot of time to compute online. So, but here we are lucky because due to the application itself, it can run in parallel with search ranking. For example, here, when the query comes here, on the one branch, we just compute the ranking. And on another branch, in the parallel, we compute the suggested queries. Then we merge together. In this case, we can mitigate the latency concern. Right? So here are some results. Even without personalization, we are already seeing a good coverage about the impression and the CTR, and like a 1% job application lift. Now with the impression, with personalization, we even see additional session success lift for passive job seekers. Okay, so that is for NRG. I don't know if I have enough time to cover the next case, but because I really want to go through the ranking part, so maybe I will just quickly go through the autocomplete. For the use case, you guys already know, right? Software, you have type soft W, you want to get a full query, right? And challenges come here. So we have short context, and we have personalization challenges. For example, we search for Google D. It could be design or data center, develop, a lot of things we need to consider. And also latency restriction is a pain. We also follow the two-stage. First, generate candidates. Then we start to do the candidate ranking. Now, for the candidate ranking, we use a language model. And at the higher level, we are going to capture the likelihood of each word. Then we will accumulate them together. Eventually, we will rank based on the overall likelihood to do recommendation. But one thing here is because online, imagine for autocomplete, when you type a word and the system needs to return a set of results immediately, every time you type a character even. So this is a big challenge for latency, and we did a lot of offline work to improve the offline model. Eventually, we are able to launch a model with 6 times speed up with regular ST model, but still the same, almost the same performance, relevance performance, I mean. Yeah. Okay, so showing some results. We have launched this on people and on job. Both are seeing great wins, and also we didn't see much latency lift actually. Okay, last piece. Matching. Matching works for both search and recommender systems. We already showed that we have different types of search recommender system. Here we have job search as recommendation. Right? But let's try to formulate the problem a bit. When a user comes to a website for search, he types a query. So fundamentally, we want to model the matching of this concept. Includes the user information, query information, and doc information. And we want to compute this kind of matching probability for every document for a specific user, specific query. this is how we do in search. In recommender system, we don't have query, only profiles, right? So that's how we do the matching based on the user and the document only. Now, informal. This is the matching score we want to compute. A function based on user features, query features, and doc features. One way is, or say traditional way is, we can generate wide features for each type of information. Use that for your ranking or for your computing, matching score compute. Right. Another way is we can send them to some kind of neural networks. Then we can generate high-level deep features and use that for ranking. And we can also choose different kind of N components. For example, we can choose CNN, BERT, or other things, or XNet, and then we can concatenate them at the higher level, eventually to capture the matching score. That's one way, right? And because we are talking about NLP, so NLP from the user feature, query feature, doc feature, they are heavily involved. And let's take a look at how we can do that. With this component, let's say this is the BERT, just an example. One way is we can always build a big network and you concatenate all the information just through in to get a feature. That's one way. Right? Another way is we can build different towers. Say we can have user network tower. We can also have query network tower. We can also have the doc network tower. Each tower is generated higher level deep features at different for each specific input. And then we will have this multi-tower network for deep networks. Eventually, we can generate a lot of interactions at the shallow network on the top level. Right? Now, why do we do that? Because once we can split that, it will be helpful for online computing. For query, this is real-time compute. But for many of the static data, we can just compute, we don't have to compute on the fly. We can pre-compute them, like a member profile, for example. Okay, and we can choose different learning losses, like learning to rank or other loss functions. Okay, so we conducted some experiments here. We have offline experiments on both search and recommender systems. For search, we are comparing for wide features, CNN and BERT. By the way, at LinkedIn, we actually train our own BERT. The reason is we want to have a more aligned vocabulary and taxonomy with our system. So another reason is because in this way we can have very flexible structure, easy for online serving. Like say we can train maybe 3-layer BERT. That's one example. Yeah. So we see offline lift from BERT to CNN on search systems. We are also seeing lift on the ads on the recommender system. Here, ads CTR is mainly about when you show ads to the user, whether the user would like to click it or not. And ad conversion is mainly about when user click the ads, whether he would eventually take some action, say buy something on the advertiser's homepage. So these are two very important models in ads recommendation. And we are seeing CNN lift. And for BERT, we have some early results, but I'd rather not release it at this time. Online-wise, we also see CNN has a good lift for both job and people in terms of their key business metrics. So with that, I just do a quick summary. In this session, I have discussed the 3 categories, NLU, NLG, and matching. I have discussed about the intention model to bridge the gap between search and recommender system. I have discussed the entity tagging that is used for candidate selection for both search and recommender systems. And the NLG that is very special to search for online assistance, and matching how to use deep neural networks to get a better ranking performance for both search and recommender systems. As you can see, we are doing a lot of components in the search and trying to improve the specific performance at one by one. Now, beyond that, how can we give a better user experience, more intelligent, more advanced? That becomes the conversational AI question answer. With that, I'm going to handle this to Liang to give the next session. Thank you.
All right, thanks for staying with us. My name is Liang. So, I think first of all, I know that you are all going to LinkedIn booth, right? After these exciting talks, so we do have a booth. So please visit us, and we will be there. So you can talk to us as well if you have other questions as well, or general questions about LinkedIn. So as we have talked about search, right? So the next step is actually going to question answering, which is a much harder problem. It's like holy grail, right? We are trying to, been doing so many years trying to conquer this holy grail, and we are still not there. Of course, whatever I'm going to present here is not going to be the same telling you, hey, we have already conquered the problem. Actually, we just started the journey. So you will see that we are still trying a lot of things here and there just to make things happen, right? And if we want to start, I want to start with traditional web search. I think we have talked about it many times today, right? So we have input as query, and then we have output list of documents, but if you look at this traditional web search experience, what can be done better here? What can be done better here is actually to deeply understand user intent, like whatever we talk about today. If we know the answer, we'll show the answer, but what happens if we don't know the answer? That is where the interaction part comes, right? It's about interacting with users when we are not sure, right? If you look at the related search, the autocomplete, a lot of things are also interactions, right? They're also when we are not very sure, then we start to show things that helps you and making sure that we can get some information from the user and then go to the next step. So if you look at the Google now or Bing now these days, they also have a way to automatically show you the answer when people post a question. And LinkedIn, we're also trying to do the same. Even on LinkedIn website, you can see that we are trying to show people's card whenever you say, hey, who is the CEO of LinkedIn? We show Jeff Weiner as a people card. And how can question answering generally help a company like LinkedIn? So at LinkedIn, we have this context, right? So say a recruiter. Recruiter comes to LinkedIn and say, I want to hire an AI engineer, right? That maybe means a lot of you, right? And the first of all, the things is brought to us and say, hey, what is the urgency? How soon do you want to find the AI engineer? And what are the person's skills, right? And which location? And are there other considerations? And then finally say, hey, these are good candidates. On the job seeker side, we can also build job seeker assistant, right? The people can say, hey, I want to find jobs for me. And then we can ask, hey, what is your career goal? What are the skills that you have and gaps? And which location? And other considerations, etc., etc. So this is an interactive experience, as you see along the way. There will be a lot of interactions, clarifications, discussions here and there, so that we're able to finally recommend the best job for the people. Right? It's similar but different, very different. Slowly going to a very different experience that we want to have. So here I want to present you a early experiment that we are thinking about and doing on the LinkedIn Help Center. Why do we pick Help Center? The reason is very simple. People generally go there with a very strong purpose or intention, right? And people have a problem to solve. And a lot of times it cannot be solved in the first batch. Because people may not be sure what exactly it is. When they have some problem, they can say, hey, this is my problem, but they may not know how is that linked to what is happening behind the scene, right? So that is where maybe a lot of interaction need to happen. And we can help the user hold people's hand and to help them become successful. So here is the example, right? People come and say, hey, how do I keep my job search a secret? See, the user posted in a way that is a very natural language way. And if you look at the original search engine that we had, it was showing like random articles. It was not very relevant, right? So we talked about it. We want to have input question in natural language, and traditional keyword search may not work well. So there are twofold of the solutions that we are trying to think about here. The first one is a question answering through the search. Meaning that even in the existing search engine, we can already do a lot of things to help the user out through the NLP technology we talked about today. The second one is more like a venture bet. How can we see if we can build actually a chatbot to help people? And I'm going to show you some demo if the network works. All right, let's start with search. So again, we talk about the input question to query and output is articles or sections of the article that contains answer. It's still a search problem, right? And the lucky thing is that at LinkedIn Help Center, we only have a few thousand candidates, although we do have new candidates added on a regular basis. What that means is that, first of all, we don't have to worry too much about latency, although we still need to pre-generate the embeddings if we use things like BERT, right? So online scoring the 1,000 document with BERT still is too slow, right? But at least you don't have a lot of candidates, which is an advantage. But when the new candidate gets regularly added, we also need to handle the new ones. So our data this is just quick summary of our data, right? But one thing to note is that we actually highlighted a lot about the queries with greater than four words or like 5 words or long words, the long queries, so that we're able to capture the queries in general, which are the natural language based. And the modeling approach is very simple to start with. We want to start with, hey, I want to consider each candidate as intent, right? So then it becomes a simple natural language query to intent modeling, right? It's like the intent prediction that we just talked about. Of course, we do need to handle the new articles. So that would means that we have to do something here. Right? So we start with CNN. The CNN approach is very simple, right? You just have two towers. One is the question, the other one is the article title or article description, and then we build the embeddings on top of it using CNN model, and finally we do a cosine similarity and we do softmax on top of that. And we use word-to-vec embedding to initialize, right? So for the new articles in the test data, what we do is we, instead of retraining the model, of course, we just simply use the embedding similarity and then just to compute based on the article content. So then we talk about, deep plus wide actually works better than just deep only, right? So deep is about the semantic meaning, and sometimes there are still a lot of things in the wide. The keyword match still play a role here. We cannot entirely get rid of the keywords match from our experience. We combine both, and that actually works better from our experience. And then we have BERT, right? We talk about BERT. BERT works better, and we also tried BERT here. It actually also works better. And if you look at the offline experience, offline model performance, you can see that BERT works the best, right? And online as well. So here I want to say that happy pass rate is something that we use as a metric for help center. What it means is that a person comes, and if they just simply left before they even so if they simply left without doing anything, that means they are not happy, right? But if they click on the article and then left, means they found the answer, right? There will also be people who actually go to the route of, hey, I want to talk to a real agent, etc., etc., etc. Then of course they are not happy, right? So happy pass here means that people who have clicked and then left without coming back, creating a case. So we can see that happy pass, of course, becomes much better after we implement CN, and control is a keyword matching here. So after we launch CN, it becomes much better. After we launch BERT, it's even better. So some more examples. You can see on the left, how to download my resume. And the answer is actually saving a profile in PDF format. You can see this is totally different. If you use keyword match, you will never be able to capture that. But by semantic matching, we're able to do that, right? Which is a great improvement. Also, I'm a recruiter. How do you find a good candidate? You can see it's actually a question. But the answer is, hey, this is about how do you find additional job candidates to help you. We have talked about this is still a traditional search engine. Right? Where the only thing we did there is just simply, hey, people post a question. Now before I was using keyword match in the backend. Now I'm using the semantic meaning of the words and doing NLP to help us find the better article for you. It's still a search, right? But how do we go beyond that? So one way we can go beyond that is saying, hey, let's do some interactions. For example, suppose I type in account here. Of course, it's not complete query, right? So with account, what does that mean? In traditional search engine, it will show you, hey, these are the articles which that matches with the query account, which means nothing, most likely. I'm not trying to serve the need because I don't even understand what you need. So these days, people generally say, hey, let's narrow down your search. Instead of show you the result, I should actually show you, first start with, hey, I think your query is not complete. I want to help you in your query. This is autocomplete we talk about, right? The restrict account, merge account, close account, which one is actually you are trying to accomplish? What is the goal you're trying to accomplish? And also, we can also directly have modules, trying to help people one click and get the answer you need if I'm pretty sure what you are doing here. You can see here we're actually doing both. And now let's go to the chatbot and see what other things can we do to make it even more interactive. So if you think about moving from search to chatbot, what are the problems that we need to solve? First, people always want to test the chatbot with out-of-scope questions. In search, you don't generally do that, but in chatbot, you do that all the time, right? For example, how are you, right? Let's try it, right? Will you marry me, right? Just try random things and see and see what you get, right? If the bot didn't give a good answer, you say, hey, this bot is stupid, I'm not going to use it anymore, right? So people do that. Ambiguity, which means that a lot of times people still use the bot's experience like search experience. Sometimes their query is extremely short, question extremely short, right? And sometimes people say premium. And then what the bot needs to reply is, hey, do you mean you want to cancel the premium account of LinkedIn, or do you want to be premium members? I'm not sure which one it is, right? So we need to get back to the user. And sometimes the question is also incomplete, right? Sometimes the question is also can be complete but still ambiguous, right? For example, the user may type in cancel account, but does that mean that the user wants to cancel the premium subscription, or the user actually wants to close the LinkedIn account? Right? Another thing that we can do is, a lot of times in our articles, instead of just directly showing people article, inside the article, in fact, there are already sections that marks the actions you take. Right? So it's much better. So it's suppose user typing edit my profile. It's going to be a much better experience to directly show you the action to take, extract it from the article section, and then tell the user exactly what to do, then just show you the link, right? So you can see iOS, maybe for desktop, iOS and Android, their actions are actually different. They're all from the same article, but it's going to be much better I show you this section rather than I show you the article link. Okay, so I talked about the different challenges that we have. I'm going to show you a high-level workflow that we have designed. Of course, you can see a lot of here are not going to be machine learned, right? It's still like human helping here, just to making sure that fits into the context and domain knowledge. But each component, we are trying to make it to be machine learned, and also we are trying to keep improving on top of that. So start with user input, and user input a question. And we'll say, hey, is this question, first thing you do is ask ourselves, is the question out of scope? If it's yes, I'm going to tell the user, to ask the relevant question, right? If it's no, we're going to do next step. Next step is trying to check if the question is complete. If the question is complete, we're good. If the question is not complete, we ask for completion. And the third one is exactly what we did for search. It's about finding the match article, given the question is complete. And then if the system returns multiple answers that are too close to each other, multiple articles with similar scores, then what we need to do, we need to remove the ambiguity here. That means there are multiple possible answers, right? Instead of showing the people the one answer is better to show people multiple choices and ask the user to pick and provide us feedback so that we can be better next time. So that's about clarification with the user. And then after that, after we know which article to pick, then we are going to extract action to take. Right? This is the one I talk about. Which device are you using, for example, right? So that we can be more precise and showing the user more precise answers. And finally, we present the result to the user, and users are satisfied. If the user are not satisfied, they're going to come back and paraphrase the question again, and then have another loop. Okay, so I'm going to quickly go through what approach we are taking. You can see a lot of things are still in the initial stage that we are finding, but this is the whole thing that end to end, right? That works. So basically the out of scope detection model. Currently we are treating this as a binary classification approach, where the positive are help center queries that are related, and negative are some queries we sampled from LinkedIn search and movie dialogue and Quora from the places that we think are irrelevant. And right now it's binary classification, either relevant or irrelevant. But even for irrelevant ones, we can in fact do something here, right? For example, we can try to, if user say greetings, how are you? We can do something. If user says I want to ask for speaking to agent, we can do something, right? There are many things that we can still help the user out, even if the question is beyond the scope, right? And incomplete question handling is actually a slot filling question, right? So for example, suppose the object is missing. Suppose I just say cancel. What do you mean? I mean, if I detect that you just only had the object, you only have the verb without object, at least I can do something here. I can ask you, what do you want to cancel? Or if the verb is missing, right? The user typing the profile. What do you want to do with the profile? We can ask with the user, right? So that's why we assume the question must contain the objects and verbs, right? If not, we're going to explicitly ask for it. So we use standard POS tagging model here. And of course, Huiji and when we talk about entity tagging, right? We can actually use entity tagging. But here, the main point is we have to build the specific entity knowledge graph specific towards help center use case, right? So LinkedIn, we already have a knowledge graph. That's why we're able to do anti-tagging very easily. But the Help Center, we have to do that so that we're able to build anti-tagging on top of that. And the question answer model, Huiji had talked about it. We have BERT plus wide model. It's the same model as what we had in search. And then finally, after we get the answers from the search engine, what we will do is we just simply handle the ambiguity by looking at the top three. If the top three are so too close, we're going to clarify with user. If the top three are far away from each other, if the top one is clearly outstanding, we're going to just take the first one, right? And we also extract action to take section from top ranked article, right? So there are like say we use pattern mining. If we know that hey HTML contains iOS, Android, etc., we're going to extract that, and human going to look at it, making sure that it's extracting the right thing, and that is how we do preparation of all the articles that we have. And then finally, we follow up with the user. All right, so I'm gonna do some quick demo. Oops. We're gonna see how it works. So as you see, that can everyone see the font? Is it okay? You can see what I'm typing there. Make it bigger. Is it okay? Better? You can see I already typed how are you, and they say, hey, this is out of scope, right? Of course, I can handle it by saying, hey, greetings, right? This is what we talked about, okay? And next thing, I'm gonna type in how to ask for recommendation and see what the bot says. Okay, looks like we have some. Let me refresh. Okay, awesome. VPN, let me connect to VPN. As you all know that every time people do demo, there are issues. But hopefully I can connect to VPN again. All right, we're back. So, you can see directly it says requesting a recommendation, right? See, even if I say ask for a recommendation, it actually returns requesting for a recommendation. It's different, right? Semantically, it's different. Semantic is the same, but the word is different. Suppose I say change account. Now you can see that this is ambiguous, as we talked about. It's ambiguous because the bot doesn't know that. Hey, what exactly do you want to do, right? Here it has multiple options, right? Do you mean that adding or changing your email address, or like changing your account information, or for someone on your behalf or somewhere else, etc., right? If I say profile, see what you want to do is profile because it's no longer sure. Bot is no longer sure what you want to do. And suppose I say I want to edit. You can see that the bot is able to capture the previous context because I type in edit. I didn't say edit profile, I just say edit. It's still able to handle it. And say which device are you using? We say Android, and you can directly see the results. Right? Suppose I say profile again. Even I say deactivate. See, it's different, right? I'm not typing view, edit, or hide. I'm typing deactivate. You see, temporary disabling account, which is a little bit different. Word perspective, but semantically is actually matching. Suppose I say approve group members. You can see that manually requesting, I'm going to type this one and see the results get out, right? So this is just a quick demo of what we have as the chatbot for the help center. You can still see there are a lot of things to be done, but we already have the end-to-end flow, right? And also we are able to capture the semantic meaning of the people's questions, which is very difficult to do. All right. We have talked about many things, right? So I want to conclude with some of the lessons we learned and future trends. So I want to start with the data. Data is very important. So we have, at LinkedIn, we use human label data, we use the user behavior data, we use a lot of different data, right? And we also talked about the automatic data generation using GAP, so that it become more consistent of in the training phase and prediction phase, right? Which is all great, right? So how do we combine all this data together so that we can have a good model that's still a challenge, right? Because we do have different business objectives. So user behavior generally, in general, give you the good business objective to optimize for. But even when you start combining with human label data or with GAN, then you may start to lose some of the business objectives. So that's actually a trade-off there. So that we need to be carefully taken care of. And then go to training and serving. We do have a lot of product. We have many different research products. How do we make sure that we can leverage the data from different research products and then being able to train, pre-train the model even before we launch a product? That'd be pretty cool, right? We also have there's also always the hyperparameter tuning, structural learning, which is always a challenge with such a complex modeling system and serving system. Internationalization. So LinkedIn is a very international company. We serve a lot of languages, right? More than 18 or probably 20, even more languages. So how do we make sure that we have a good model behavior, right? Good relevance for every language? That is always a challenge, right? That's why transfer learning, multilingual learning is very important for us to keep making progress there. Reinforcement learning is also a very new area, right? There are a lot of research these days talking about how do we use long-term reward optimization so that we are able to not only optimize for the short-term reward, but the long-term reward from the feedback loop that we receive from the users. Recently, we have see some papers. This is something that we can directly, see some papers in the industry or literature, we can actually directly apply those methodologies at LinkedIn or even further advance the technology there. And multi-turn question answering. As you see, although the demo I just showed has some multi-turn, but that's not from reinforcement learning, right? Because actually you can do reinforcement learning and achieve much better results there. And finally, it's about the model debugging and interpretation, fairness, privacy, right? Actually, at this time, we do have another talk from LinkedIn going on, some people from LinkedIn going on talking about privacy and the fairness and the model interpretability at LinkedIn, right? So, I would encourage you. This is a very important thing that LinkedIn is trying to invest, this is also something that we really think is so important and it will advance our technology further. Okay, with that, I'm going to conclude, and thank you very much for attending. If you have any questions, now is the best time for you to ask. Yeah, thank you.